Ling's Chih. It's Teng, okay, sorry. And he's going to talk about galaxy source counts and 7.7 micron, 10 micron, 15 micron.
Okay, hello everyone. My name is Teng from National Tsinghua University, and today I'm talking about the galaxy source count at 7.7 micron, 10 micron, and 15 micron with ZLST. So since ZLST released their data 2 months ago, there have been many scientific results you should frequently seen on archive or somewhere, but not most of them are published and accepted. So this is very fresh work from ZLST work from Taiwan, and I believe this is the first data paper. Then we just submit 1 month ago and got accepted 1 week ago. You can check the website. This is just a screenshot. So let's go to the introduction. What we count galaxy in mid-inference. So first, galaxy count, or we say number density, is directly observable for inferring the galaxy evolution, because we just count the galaxy, how many galaxies on the sky, then we use this to infer the evolution of them. Then the mid-inference galaxy is very interesting because such galaxy like starburst or active galaxy constellation is have a very high star formation rate. So if you study those galaxies, you can further to understanding the cosmic star formation history. So there's previous inference space telescope like Akari or Spitzer are already doing this mid-inference galaxy count. But why we are doing this for ZLST again? The reason is very simple. The ZLST resolution and sensitivity is very super. You can see in these two figures, if we just use Spitzer's image to count the galaxy, we have missed many of them because they are so blurred. So I need to use the ZLST image to count the galaxy in those images to obtain those many galaxies we have missed before. Then we use the streaming printer from the ZLST mirrors image, and this image composed of 2 components. One is the foreground galaxy NGC 9320, and other is a galaxy group. So this image is very beautiful, but when we're doing the galaxy source count, actually we don't need this streaming printer because we want to count the galaxy in the field. So these 2 images are the raw bit file we composed with these 3 filters, like 7.7 micron, 10 micron, and 15 micron. Then we just drop the galaxy in those red regions and count the galaxy in the remaining part. But we still have around 4 Archimedes square area, so it's still large enough to us to count the numbers. So we use the software called Source Trader to generate the source catalog. We following the ZLST public catalog to use the 7 temperature graph and use this parameter to run the source tracer. And this figure is just a sample for our source detect in the image. But none of the image or source tracer are perfect. So how reliable is our source count? To measure this, we just estimate the convenience of as a function of the flux. So to reach this, we at each class we randomly cache some PSF sources, and we rerun the source tracker to check whether those artificial sources can recover by the software or not. Then we calculate the completeness. So the 80% completeness is shown as the loss value, and for comparison, the Akari 7 micron 50% completeness is around 100 times of this value, or you can see in this image. So the sensitivity is very different for them. So based on this very superior sensitivity and resolution of AWST, we can go to our result. This is for 7.7 micron. So this red part is Visa and blue is AWST. Then this blue part is never seen before because it's just overlap the brightest end of AWST just overlap with the faintest end of Visa. And for 10 micron is the same. So we compare for Akari and also for 50 micron. So what we can learn from those results? First, our source count has a very excellent agreement with the model showing this orange curve and black curve. And we also have a well content and expand those previous observation from Akari, Visa, and ISO test code to a micro jump speed labels. This is about 2 orders of magnitude different than ever before. And based on this very good consistency, we can confirm our understanding on extremely faint gases in mid-infrared. And based on the result, this can be the first step for establish the luminosity function and the evolution of those mid-infrared gases. So, as a short summary, we obtained the first mid-infrared gases come from the early release observation image of AWST, and we estimate the completeness of our sources. Then we find our results not only consistent to the previous observation, but also with models, and even with the 100 times deeper than ever before. So this is just a number count, and number count cannot tell us anything because just a count. So, and every things like redshift evolution or luminosity evolution are degenerate with this. So with what is the physical implication? You can refer to the following talk by Song which is also our group member. And if you are interested in other ZLC related topic, you can see also this poster. So that's all of my talk. Thank you very much.
Thank you. Any question? Yes, thank you.
I don't know if this is actually for the next talk, because in the previous slide you showed the result is consistent with the models, the published models. Yes, the top item. So can you comment on what goes into those models, or these will be discussed in the next talk?
These two, maybe I can introduce these two models. So this orange curve is from the N-body simulation, Cosmology simulation, and they just use the simulation data to construct this source count curve. And the red curve is the empirical modeling from old data. And I think next talk we'll use our new data with those faint gases to update those old model parameters. Thank you.
Any question? No? Yeah.
Thanks for our presentation. And you mentioned that when you count the sources, you have to remove the foreground galaxies. So I'm curious about how to define the boundary of the foreground galaxy, and do the results change if the boundary is different?
Yes, so it's very good question because we just select this object by eye. You may think this not scientific, but we try to exclude the sources that is diffuse or extended. Then remain the galaxy object in the field. But for stimulus printer is not so good for those counts. But in the poster we have also applied this on COS field, which we doesn't need this mask for the image. And we found the result of our this work and the COS field result is consistent. So I think it's okay.
Okay, thank you, speaker. We have next. We have